Gentlemen, and welcome to the Space Telescope Science Institute Public Lecture Series. It is my pleasure to be your host. I am Dr. Frank Summers of the Office of Public Outreach. As you come in, as these gentlemen just are right now, there are lithographs on the table that you can grab and take home. Tonight's lithograph is of Interacting Galaxies ARP 273. Our speaker will be talking on the development of galaxies in the universe, and this is a very interesting pair. If you would like to know more about it, turn over in the back, and we have a few paragraphs telling you about the state of ARP 273 and where you can go to get more information. Our speaker tonight, Katey Alatalo, is talking about 100 ways to die in the universe, okay? She promises death and destruction here tonight, okay? Astronomy usually doesn't have that much action, but we're going to have it tonight. Next month, chasing supernovae with Kepler. The Kepler satellite was out there to find planets. But you can also use it because it can monitor the brightnesses of stars extremely carefully. You can also use it to find supernovae. And Gautam Narayan will be telling us about that on October 2nd. November, and because Election Day is the first Tuesday, we will be skipping to the second Tuesday, November 13th. And we'll talk about exoplanet atmospheres, Giovanni Bruno. Now, I got an email last week saying he might not be able to make that. So this is going to become a TBD probably next week, as soon as I get in contact with him again. So I got some work to do. As you can tell, because December is listed as some intriguing topic by some amazing speaker, so it's difficult to get astronomers to commit over the summer, so I wait until September to get them to commit. And so, yes, I'll be sending that email out this week or next, okay? Don't worry, I always fill up the schedule. All right, and you want to find out what these speakers are when I do fill up that schedule, you go to our website, go to your favorite search engine and type in Hubble Public Talks, you'll find us. Or we have this hubblesite.org, Go Talks to find us. We have our list of the upcoming lectures. We have the links to the live webcasting and YouTube events. We also have our archives back to 2014 on YouTube and all the way back to 2005 in the webcast archive. So our guys in the back have been doing this for, what is this now, 13 years? All right, this is amazing stuff. Yeah, give them a hand, give them a hand. They deserve it. Also on our website, you can sign up for our email list, which is basically just reminders of the talks and telling you when the webcasts are posted on YouTube. Okay, so yeah, that's the announcement. Sign up at the website. If you don't like signing up on the website, you can always just write your email address on a piece of paper and hand it to me at the end of the lecture. If you have comments or questions, we have an email set up, publiclecture@stsci.edu, and you can use that. Our social media, for those who do it, we've got Facebook, Twitter, YouTube, and Instagram, not just for the Hubble telescope, not just for the Webb telescope, but also for the Space Telescope Science Institute. So we've got 3 different brands that we are marketing here, and we actually, the folks who do this do a really good job of getting an interesting mix of things across the various channels. I do not, however, do an interesting mix of things. I rarely post on mine. Something I should do more of, but frankly, there's just too much cool things to do to spend all my time on social media. So you can follow me, but I will not be on there all the time. The weather is finally permitting. I got the email from Irini today, and yes, the observatory will be open after the lecture, okay? So the Maryland Space Grant Observatory, Irini will come here toward the end of the lecture. She's probably watching this on YouTube right now. When the questions start, she'll come, and if you would like to go to the telescope, to look through the telescope tonight, it may be warm, but we'll meet down here in the front at the end of the lecture, okay? All right. And now the news from the universe for September 2018. Our first story tonight, ultra large, ultra deep, ultraviolet. Yes, Hubble is going ultra here. Now, what am I talking about? I'm actually talking about the legacy of Hubble's deep fields. And the first deep field was released in 1996. This was done with Wide Field Planetary Camera 2, hence it has the chevron shape to it. And it was a magnificent step in cosmology, because we really didn't know what we would see when we looked at the universe this deeply. When we used Hubble to expose for a week's worth of exposure time, there were arguments amongst the cosmologists as whether this is a total waste of Hubble or, hey, we're going to find out something really cool. Fortunately, it was the second one. We did find out something really cool. We found 3,000 galaxies in a tiny, tiny, tiny patch of sky. And so what these are, we're seeing galaxies all the way across the universe compressed into a single image. We're seeing galaxies deeper and further into the universe than we had ever seen before. So, of course, when we got a new instrument in 2004, the Advanced Camera for Surveys, we started doing some surveys. And one of the surveys we did in the camera was in 2002. In 2003, the Great Observatory's Origins Deep Survey in 2003. This was 15 pointings of Hubble across, and with a detector that's twice the size of with PIC 2, so 30 times the area on the sky of the original Hubble Deep Field. Well, when you do that large of a region, you can't go extremely deep. So they chose a special region in here in which they really, really went in, and they did a million seconds of exposure time on it, and this was the Hubble Ultra Deep Field in 2004, the deepest visible light exposure of the universe taken to that time, and remains to this day, really, because the only thing deeper are updates to the Ultra Deep Field. And so this had 10,000 galaxies and really started letting us look out towards the edge of the cosmos. Well, in 2009, we had another servicing mission, and that greatly improved our infrared capability. So in this region here, which is where the infrared detector covered, we did the ultra deep field with infrared in 2009. And infrared is extremely important for cosmology because the light from very distant galaxies is redshifted. Its light is stretched, and it goes from visible light, even from ultraviolet light, into the infrared. So if you want to see the most distant galaxies, you've got to look in the infrared. Well, we also improved the ultraviolet capabilities at that time, but we didn't get around to releasing and doing those observations until 2014, where they had the Hubble Ultra Deep Field with ultraviolet. And this, I like to call this the multi-wavelength deep field because it's got ultraviolet, visible, and infrared. It covers the entire panoply of wavelengths that Hubble can look at. And it was really an amazing piece. But it showed us that we still wanted more. So a bunch of astronomers proposed to do this, but on the Hubble Deep Ultraviolet Legacy Survey. And we just released those a few weeks ago, the HUDV, two fields. This is the north field, and this is the south field. And I gotta say, when you look at them, you go, okay, yeah, more deep fields, right? Yes and no, okay? Because, first of all, the ultraviolet is extremely important because it shows us where stars are forming, okay? Newborn stars, the most massive stars, shine brightly in the ultraviolet, but they only do so for tens of millions of years. So it's just the brand new newborn stars that can be found with ultraviolet. And ultraviolet can't be seen from the ground. Okay? We can't do good ultraviolet astronomy from the ground. We have to do it from space. So having Hubble do these ultraviolet fields is extremely important. Furthermore, the size of that Hubble Ultra Deep Field ultraviolet is only that. And with these two fields, we have 14 times more surface area on the sky, 14 times more statistics of the ultraviolet galaxies. So what we're doing is we're looking at the ultraviolet, which we can see most clearly in the nearby galaxies, but in the far galaxies, where the ultraviolet has been stretched to the visible or the infrared, we now have a calibration data set of the nearby stuff to compare to what these objects look like in the visible or the infrared, which is really the ultraviolet for them. because their light has been stretched. So we now get a much better comparison of what these distant galaxies might be looking like in the ultraviolet compared to this. Now, this was just the announcement that the Ultraviolet Legacy Survey has completed their observations. It's not the science results yet, but it shows that Hubble is putting together what we call these legacy projects, these important data sets that only Hubble can do during its last years. Because we know Hubble, hopefully it'll last a long, long time. But while we've got Hubble and it's working really, really well, we want to make sure we get these legacy projects done that really have a great data set for astronomers to study in the future. Our second story, the master retires. There's been a gentleman, his name is Zsolt Levay, and he has worked here for 35 years. Now, those of you who do the math, Hubble has only been around for 28 years, okay? Zsolt has been working here for 35 years. For the last 25 of them, he has had his hand in almost every single Hubble image you've ever seen. He is, I call him the master in terms of master retiring. He's what's known, his job title was Master Image Processor. So the look and feel of all the Hubble images has gone through his computer for the last 25 years. And he has really put his stamp on it. And he's really well loved around here, but he retired last Friday, and we had a big party for him. For me, it's especially important because, he was part of our visualization team. This is the four of us holding a piece of IMAX film. This is the four of us who basically worked on the IMAX film Hubble 3D, and that's some of the test negatives from IMAX Hubble 3D. And Zsolt was a big part of it. And so although I've worked with him for 17 years, I worked extremely closely with him for about the last 10 years on our visualization team. He's a consummate professional, and he'll truly be missed. What's he going to do? Well, he also, not only working with space images, he also does nature photography. And this is an exhibit that he had in Jackson Hole, Wyoming, which then came to Baltimore this summer, called Celestial Terrestrial Convergence, where he's comparing a bit of the Carina Nebula here to star trails over some rocks in Zion National Park. And it's the combination of the terrestrial photography that he does, as well as the celestial imagery that he has processed that's part of this art exhibit. And he's going to spend a lot of his time now on the terrestrial part of it, working with astrophotography. As I said, he's been here for several decades, and we just wanted to wish him well. And congratulate him on his success in the years past and wish him well in the future. All right, our featured speaker tonight is Katey Alatalo, who tells me she grew up in Michigan, and she stayed in Michigan for her undergraduate work, going to University of Michigan.
Go Blue.
Yeah, she has to say go Blue, so I'll make sure that the people on the webcast can hear that, okay? All right. Their rival would be Ohio State, right? Because I was at Michigan with Gus Everard, and I was there during the week with the "Oh How I Hate Ohio State," going all over the place. So that was one of the few things I remember from the week or two I spent there. Anyways, Buckeye fans, we love you too. We just happen to have a Wolverine here tonight. She did her graduate work at the University of California, Berkeley, where I also did my PhD, although separated by just a few years. And she came here last April to work in the INS on, what's the acronym here? Near
Imaging and Spectroscopic Survey.
NIRISS. Spectroscopic. Yes, there we go. I haven't gotten the James Webb acronyms fully down yet, but we'll get there. And she's here to talk to us tonight. All right, 100 ways to die in the universe. Ladies and gentlemen, Katey Alatalo.
Frank, with an intro like that, I'm not entirely sure I'm going to need some of my slides. Thank you. So yes, I'm going to take a walk with you through showdowns, brawls, and zombies in the life and death of galaxies. So Frank has already actually covered this. This is me, born and raised in Michigan, a Wolverine, a proud one. Don't worry, I do actually also appreciate people from Ohio State, though there's one Saturday a year I might not so much, but don't worry. I then went to California and spent a long time in California, and now here I am in the great state of Maryland. I would call myself a galactic archaeologist, if I were to put a name upon it. I will say I have never had to go into any caves and switch things and dodge boulders, but some of the things I've had to do with radio telescopes were a bit death-defying, so, maybe a little bit Indiana Jones, but not completely. So again, when I say galactic archaeologist, what I mean is I study galaxies. I search for the imprints of their past interactions on their present-day selves. I look through huge data sets, looking for a special subset of galaxies that are dying right now. And I use the size of the universe as a time machine to look at galaxies from 10 billion years ago. And the great news about the news today about the Hubble ultraviolet ultra-deep field is that that actually is one of the kinds of time machines I like to use, because of the fact that when you are looking at distant galaxies, you're also looking at old galaxies. But I guess we will actually start with a history lesson here. I start with Charles Messier in particular, who was an astronomer, and a lot of people know him as basically putting together a catalog of failures. That is, not failures in what they were, because again, he categorized some of the open star clusters, globular clusters, planetary nebulae, star-forming galaxies, star-forming nebulae, but it was mostly because he was looking for comets. So to him, he got new science out of a failed project. That failed project was finding more comets, because he said, oh look, oh, it's not a comet. Not a comet. Shoot, not a comet. But for us, again, his catalog is very important because it's some of the near sky objects we can actually look at and see in great detail. Sometimes we can see them with our naked eye, and sometimes it takes very little, something like binoculars, to actually see this. But to me, the actual start of understanding what the universe was came from this gentleman right here with his pipe, Edwin Hubble. I think you might have heard that name. This gentleman was the namesake. And I was lucky enough, when I was a postdoctoral Hubble fellow at Carnegie Observatories, I actually got to work at the place where Edwin Hubble did his science, which was pretty cool. I got to see his office, which now the director of Carnegie Observatories uses. And I actually got to see this, which is a plate taken by Edwin Hubble of the Andromeda Galaxy, where that up there, that red var, is Edwin Hubble's handwriting, because he found a variable star in the Andromeda Galaxy, which told him that the universe was beyond the Milky Way. So not only did he discover this, he actually also put together something that we use today for galaxies, which is he put together the Hubble sequence of galaxies. So here is the paper from, I think this was in 1923, maybe 1926. The classification employed is based on the forms of the photographic images. About 3% are irregular, but the remaining nebulae fall into a sequence of type, forms characterized by rotational symmetry about dominating nuclei. The sequence is composed of two sections, the elliptical nebulae and the spirals, which merge into each other. So here is what the Hubble sequence actually looks like in modern times. Here is a really nice version of it, made in part by the help of the Zooniverse. But let me show you what Edwin Hubble published in 1926 in his book. 1926, folks. I'd say he did a pretty good job. Now, he accidentally flipped the order. He thought that the elliptical galaxies were the ones that morphed into the spiral galaxies. But that is all that he got wrong, because as I said, as I showed you just previously, right? Pretty good. So, as Edwin said in that original paper, the Hubble sequence breaks into types. Over here you have spirals, and over here you have early type galaxies. Now again, early type is an old-fashioned nomenclature coming originally from that Edwin Hubble mistake, which we still use today, to unfortunately confuse the public as well as our students. But early type galaxies are actually the old galaxies. So a typical spiral is disky. It has spiral structure, it's blue in color, and it's forming stars. Early types actually break into two different types. You have typical ellipticals and lenticulars. This is a lenticular galaxy, this is an elliptical galaxy. The thing that differentiates an elliptical or an elliptical and lenticular / early type galaxy from a spiral is actually that it lacks that spiral structure. So, in this sense, the smooth structure is what classifies you as an early type galaxy. Lenticulars are disky, ellipticals are ellipsoidal, they're red in color, and they're non-star forming. So, again, we break it down. Spirals are blue, they have disky structure, visible spiral arms, star forming, and right now 77% of the galaxies in the sky are spirals, blue, star forming. Again, this is typical. Ellipticals are red, they're ellipsoidal in structure, smooth light distribution, quiescent, which basically just means non-star forming. Quiescent means quiet. So if I slip into astronomer speak, I just wanted to make sure when I use the word quiescent, you know what it means, and they tend to be more massive. Why is it that I keep saying the word star forming when I'm talking about blue, and I keep saying things like quiescent when I talk about red? The colors of galaxies, for the most part, save for dust, which is actually important, come from the colors of the stars that the galaxy is comprised of. So a stellar population, a young stellar population, again, something Frank said earlier, is blue. It's coming from young, hot rock star stars that are going to live hard, rock hard, and die young. Because they are burning up their star-forming fuel so fast, they get very hot in temperature, and that temperature makes them blue. On the other hand, older, smaller stars are red in color, like that, which is why elliptical galaxies would have a lot more of these stars that have been taking it easy their whole lives, not really big, burning their hydrogen sort of at a low level. It's why these galaxies are red, because they're cooler, which means they can last longer, and they're older. And the reason this works in a galaxy is because these blue hot stars are so dominant to the light in the galaxy that even if you have a lot of these older red stars in your galaxy, the second you have blue stars, your galaxy is going to look blue. So, when I talk about star formation, I also kind of want to tell you what I mean, because again, we're having to get into the murder mysteries of what kills galaxies. So when I observe star formation, what you're usually looking at is a hot, young, newly formed star cluster, and around that star cluster is all of these clouds, these parent clouds that created these stars. And what you see is this hydrogen and this dust that is re-radiating that hot ultraviolet light. That hydrogen is now getting irradiated and is re-radiating that in the optical from H2 regions, H2 Roman numeral rather than H2 subscript. And the dust grains, where again they're absorbing this ultraviolet light from these new hot young stars, is getting re-radiated in the infrared. So when you think about how to tell if a galaxy is forming stars, you now know that they're blue in color. But you also now know that there might be some other signatures. For instance, you might see these hydrogen lines, or you might see dust. And on top of that, you want to look for things like this H2 gas. So when we look up in the sky, we see this. Well, I should point out from Maryland for a while, unfortunately, we haven't been seeing this. We've been seeing a lot of clouds, getting a little rain in our faces. In Los Angeles, where usually it is pretty dry, I will say, we did not see this. We saw a lot of city lights. But if we're very lucky and we go out into the desert or we go to a place that's low light, we could potentially see this. My favorite place to see this is probably the Chilean desert. But you don't need to get to the Chilean desert to see it. You could see this in Wyoming and on particularly dark nights in Michigan. But that's not what everyone sees when they look at the Milky Way. It's what our eyes see because our eyes process optical light. But our telescopes and our instruments give us a much greater picture of what the Milky Way is. We know what the Milky Way looks like in gamma rays, X-rays, optical, near-infrared, mid-infrared, infrared, molecular hydrogen, radio continuum, atomic hydrogen, and even lower frequency radio continuum. And the reason astronomers like to do this is because each one of these can tell us something a little bit different about the universe, a little bit different about our world. So the ones I think about are, I like to think about this one. I like to think about where the molecular hydrogen is, where the cold, dense gas is. Because where the cold, dense gas is, that's actually where you're going to find your stellar nurseries. That's where you're going to find the places that you are birthing new stars and keeping your galaxy blue and vibrant and star-forming. How we see these different wavelengths is with a lot of really cool telescopes. I obviously have not seen all of these in person, given that this is in space and I am not an astronaut. But astronomers get to use an incredible set of tools with which we can actually look at these different wavelengths to understand different things about the universe. How do we find star formation? Well, one thing we can look at is the ultraviolet. This is the Whirlpool galaxy. This is done by Galax. There are images of this with Hubble that are significantly better than this. But because ultraviolet light is coming, again, from very hot, very young stars, you're able to trace star formation with it. You can also trace it in H-alpha. Again, if you think back to that little diagram I showed you, one of the things that these hot stars do is they irradiate the gas that is around them, and that gas being radiated will re-radiate that ultraviolet light that it absorbed in lines, including the H-alpha line. And finally, you can see star formation in dust, this image being an image of the Whirlpool galaxy from Herschel. And what you can see here is, again, where you have those gas envelopes that are around those stars, you also have dust. And that dust is taking those ultraviolet photons and re-radiating it as well. Okay, that's great. But what about the fuel? How do you form those stars? We now know that you can look at ultraviolet light, you can look at optical light to some degree, you can look at spectra, you can look at dust, and you can find where the stars are actually forming. But what if you don't want to just think about the product? What if you want to think about the source? Well, where you see young stars, you have to have fuel that is forming the young stars. So first thing you do is you look at where the young stars are. You can also look where the dust is. Because again, the dust is in those envelopes, those cold pockets of gas, with that gas re-radiating. And finally, you can look at the molecular gas. In order to form a star, you need to be in gas that is both dense and cold. Because it has to be dense because you need it to be able to overcome gravity and collapse upon itself to form that star. And the thing about hydrogen is you're not going to find hydrogen, just atoms of hydrogen, in places where you don't have cold gas. You need to find molecular hydrogen. So molecular hydrogen makes up about 70% of the mass in our universe, and is also, I guess it's not molecular hydrogen. Hydrogen makes 70% of the mass of our universe. Molecular hydrogen is where you form stars. But there's this problem with hydrogen. The problem with hydrogen is when it is trying to radiate, when it's spinning, it doesn't have a dipole moment. That means that it's really, really hard to detect it directly. But it has this neighbor. And I know in our world, carbon monoxide is not so great, but for radio astronomers, this is a wonderful molecule. It's wonderful because it forms in exactly the same environments that you find molecular hydrogen. That is, if the conditions are ripe to form molecular hydrogen, the conditions are ripe to make stars, the conditions are also ripe to form carbon monoxide. Carbon and oxygen are also two of the first molecules that formed in stars. So really early on in the universe, you had plenty of carbon and you had plenty of oxygen. But the thing about this molecule that's even better is that carbon and oxygen have a big dipole moment. So the second they start rotating, they radiate, and we can pick that up. We can pick that up in radio telescopes. So, despite the fact that unfortunately the thing we would want to detect most, molecular hydrogen, sort of out of our reach, carbon monoxide is not, and it is best friends and neighbors with that molecular hydrogen. So, we use radio telescopes for it. Carbon monoxide is brightest at a frequency of about 115.271,202 gigahertz. Yes, I've had to type that number into a lot of programs to process data, which is why I remember it to that many significant figures. But the idea is this is something that you can see in radio. And with radio telescopes, you're actually able to monitor it. This video was taken of, unfortunately, the now defunct Combined Array for Research in Millimeter Astronomy, which was in the desert just outside of Mammoth Lakes in California. And CARMA was a great instrument for finding carbon monoxide in galaxies, and thus finding molecular hydrogen and just finding star-forming fuel. And now, even better, is in the Atacama Desert. ALMA has been out there doing incredible revolutionary things, where it's being able to find carbon monoxide not only in nearby neighbor galaxies, but out to the beginnings of the universe. So what does this all mean? I've now told you about how I like to observe stars forming, old stars, young stars, red stars, green stars, blue stars. And I've told you how I want to look at the star-forming gas. But what do you have to do to see a galaxy march from this vibrant spiral-like thing to this red and dead thing? We've thought of a few ways. And I'll say, maybe galaxy evolution astronomers are some of the most macabre astronomers, but I like thinking about this, even if it's just to think about how to prevent it. So, if you're a spiral galaxy, how do you become an elliptical? How do you lose the ability to form those new young stars? How do you lose that star-forming fuel? You can fall into a cluster. You can go through a merger. You can be in a galaxy group. You can have death by black hole and galaxy shapes, which I don't think I will talk about today. Don't worry, I will talk about most of these. So, death by strangulation, i.e., falling into a cluster. Galaxy clusters are huge conglomerates of a lot of galaxies that are in basically a big pocket of hot gas. This represents our hot cluster X-ray gas. And because of the fact that they are gravitational sinkholes, galaxies that are near clusters are pretty much doomed to become part of the clusters. So unfortunately, this little guy, galaxy, has been caught by the cluster. It is now falling into the cluster gas. When it falls into this, ram pressure stripping actually starts to strip all of that nice star-forming fuel out of the galaxy, and it pulls the gas out of the system. Without the gas, unfortunately for that galaxy, It's not going to be forming stars, so it's not going to be blue anymore. Because all of a sudden, those yellow and red, sort of easygoing stars start to dominate the light in the galaxy. And to us, the galaxy actually looks green. And then finally, upon losing all of its gas, the galaxy stops being able to form stars at all, and it becomes red and dead. It fades into becoming red, where again, the only stars you're seeing in it now are those older, easygoing, smaller stars that are 10 billion years old, as opposed to those young supernova rock star stars, which are going to die in about 50 million years, 10 million years. They don't last long. And just in case you wonder if we've ever observed this, we have. We've actually seen this process taking place. I don't know whether you can see these little filaments here, but those are actually the places that the gas is being stripped out of that galaxy as that galaxy falls into a cluster. We call them jellyfish galaxies. Who said astronomers are not creative in their naming schemes? So it's why, when you look at a cluster like this, most of what you see are these red and dead galaxies. Now, there's something fairly special about clusters, is that you actually get to magnify background galaxies. But for the most part, the galaxies that are in this cluster have had all of their star-forming fuel gone. They have not been able to form new stars. Those new stars have not been able to return the galaxy to looking blue, so those galaxies now look red. Death by battle, mergers and interactions. So, let's say you take two equal mass progenitors. Progenitors just means original galaxies. Either spirals that are elliptical, so you let them encounter each other. Their merger is going to produce an elliptical galaxy. And the colliding galaxies have explosions of star formation. But in those explosions of star formation, they basically use up their gas really, really quickly. So this is a simulation done by Phil Hopkins, which shows a video of what this process looks like. Now I should point out, up here, you can see the time scale, 1 gigayear. So unfortunately for us, we don't get to watch this fireworks show in real time. So this is sped up by, well, a lot. As you saw, we started with two disk galaxies. This is not looking so disky anymore, is it? Does it have spiral structure? That thing that tells us whether or not we consider it a spiral galaxy? Not so much. There is still a dust lane, because again, we just smashed two gas-rich galaxies into each other. But slowly but surely, that dust is being consumed by star formation. And the thing that's great about this is that we know what we think we should see. Again, you saw the simulation. And we see this in the real world. When we look at galaxies, we see absolutely beautiful images of galaxies as they're colliding with one another. You see the explosions of their star formation. And again, you see them at all different stages. Thank you, Hubble. So, why is it that colliding these two galaxies, you know they have hot gas, they're exploding in their star formation for a while. Why is it that they turn into this red and dead galaxy? Well, it has to do with gas. So I'm playing the same movie again, but this time I'm showing you two images. I'm showing you the one that if we were, omniscient energy creatures who lived for billions and billions of years, we might be able to see in real time. Unfortunately for you and me, that is not the case. And over here, I'm actually showing what would happen if you had eyes that could look at the gas in the galaxy. The hot gas, that is gas that is traced by X-rays. The warm gas, which is traced by things like ionized gas. And again, the cold gas. That blue gas is the most important gas in this system, because that's the gas that's forming stars. And what you can see is as this merger keeps going on, yes, you're getting these little explosions of star formation, but all of a sudden, all of that warm and cold gas, now you're seeing is really either concentrated in the very center as it's forming more stars and just finishing off, But mostly, it's becoming hot gas. And unfortunately for star formation, hot gas does not form in stars. So what actually happens here? Why does it happen like that? Well, I have a handy-dandy schematic here. First, you have your isolated disks. You go through the first interaction. There's a coalescence, that is when the two galaxies finally smoosh into each other. There's a gas blowout phase, a quasar phase, which might be previewing to the next part of my talk. Once a quasar phase has removed all the gas, you get to the decay/dying phase, that is the post-starburst phase, until inevitably you march into the red and dead phase. Death by melee. So we've now talked about clusters, which is hundreds of galaxies, and one galaxy falling into that and being doomed to lose all of its gas. We've talked about a pair of galaxies having a battle to the death for their gas. Now we're going to talk about something right in between. The fun thing about the right in between for astronomers is it's actually one of the most complicated things to model. Because two galaxies you can kind of model together. A really big massive cluster can actually be modeled as just that one little dinky galaxy in the big cluster. Unfortunately, this galaxy doesn't just care about that galaxy. This galaxy cares about that galaxy, and this galaxy, and that galaxy, and that galaxy. So when we say compact group, because we're astronomers, the first way we actually define this, like Edwin Hubble, was a small, relatively isolated system of typically 4 or 5 galaxies in close proximity to one another. When Paul Hickson actually did this, he was not looking at spectra, he was not comparing redshifts, he did not have 3-dimensional information on these galaxies. He had images. And from those images, he basically looked at places where he saw a few galaxies that were close to each other, and then he carefully calculated the brightnesses of those galaxies to see if they were pretty much as bright as each other. And he came up with a list of 100 compact groups, which we now call Hickson compact groups. And of those 100, I think that 93 of them, when we went back and took spectra so that we had their distances, we found to actually be correctly identified as compact groups that were together. So I'd say that's pretty good for somebody having just, images. They have a high fraction of dead galaxies. They have evidence of tidal interactions. And again, the high density means they have lots and lots and lots of interactions with each other. They get the worst of both worlds. There's hot gas in those systems, so they're getting that hot gas stripping away some of their gas, and they're also having interaction after interaction after interaction, which is, again, pulling their gas away from them. So they start as a loose group. At some point, they become a compact group. The star formation fuel starts to be dispersed again. When you have an interaction, a lot of your cold gas starts being heated and becoming part of that hot gas halo. The galaxies evolve into ellipticals and lenticulars. Again, a big X-ray gas bubble is shown. And maybe, we're not sure, but maybe compact groups can actually make giant ellipticals. Most of the time when we see the ultramassive elliptical galaxies, those are the ultra big red and dead galaxies, we see them in the center of clusters. But once in a while, you actually find these very rare things in the field, that is, not around these big 100 galaxy clusters, but by themselves. And so one of the big questions we've asked is, how do they get there? And it looks like it's very possible that these compact groups are one of the ways to do it. And again, death by black hole, which we call AGN feedback. So I can't help this. This is my favorite galaxy. I was a graduate student when this galaxy appeared in my life. And it was super weird, which is both wonderful and terrible for a graduate student, especially one as stubborn as I am. Because, again, from this picture, you're seeing it, it doesn't look all that interesting. But it was a mystery that all of these different things were happening in it that were very, very hard to explain. Again, it's a treasure, but it's also a Pandora's box. And I bought it hook, line, and sinker and said, okay, I am going to learn why this galaxy is doing the things this galaxy is doing. So one of the first things I did is I took a picture, I managed to convince the scientists who determine what Hubble is going to look at it for me. And luckily for me, the little graduate student, they said yes. So again, let's go back to this picture. This is NGC 1266, taken from the ground with a really good ground-based telescope in the optical with really deep observations. And this is what Hubble showed us. So yes, this is a non-photoshopped version. I'm very sad Zolt Levet has retired because I can just imagine how beautiful this would be with Zolt's incredible image processing mastery. But instead of just seeing this kind of amorphous blob, maybe a little bit bright in the middle, maybe a little bit weird, you see that this thing is really bright in the center, and you can actually see a dust cone now coming out of it. That's because NGC 1266 was one of the first galaxies we discovered that had a supermassive black hole that was actively removing the gas from the system. A lot of it. We're not talking about 1 solar mass per year here, which is about the star formation rate of the Milky Way. We're talking about the fact that this little black hole is doing some work. This is 100 solar masses per year that it's managing to move around in the center of this thing. So, the next thing you do, again, another gorgeous Hubble image. This time I took it in the near infrared, which is a very good way to trace stars in particular, to look and see if I could find any signatures of some massive interaction, some big battle that took place with another galaxy like those simulations I showed you. And nah, not really. But then when you look at it and you combine not only the Hubble imaging with the radio telescope imaging, which was able to show me the carbon monoxide, thus the star-forming gas, I saw this. So radio astronomers like contours, I'll just warn you. This is very redshifted gas. So this is gas, this red blob here, is gas going 400 kilometers per second away from this point. And the gas here is going 400 kilometers per second away towards us. And that's in the middle. So when you see this, this tells you you're actually looking at an outflow. We were looking at an outflow in the cold star-forming gas. There was cold star-forming gas that this AGN/supermassive black hole was picking up and throwing out of the galaxy. So again, this picture, I hope you can also see where this Hubble image is showing you dust. That's telling you that there is cold gas at the core of a dust cone, which again, Hubble imaged for us beautifully. So that's really interesting. We've now found a way to take gas that is right in the center of a galaxy, throw it out of that galaxy so that galaxy is done. It might not be a case that gas way out here, this black hole can do much to. It has to be a really, really bright, terrible thing to affect gas out here. This should also make you feel pretty safe. We are 8 kiloparsecs, that is like way out here compared to the center of the Milky Way. So it would take a lot of really crazy stuff to happen at Sagittarius A star, the center of our own galaxy in the supermassive black hole there, to do anything really significant and terrible to us. So that's, again, great for us, annoying for astronomers. Because for astronomers, if you want to get rid of gas here, because again, we know these galaxies are red and dead, you can't do it with something there. If you move the gas in to there, we now know even a little, wimpy, not super powerful black hole can do a huge amount. So that's great. It's wonderful when you find a thing that starts to answer some of the questions you have. But there's a problem. Like any case study, it's one thing. Has anyone ever fit a line to a single point? You should not do that. That's bad. Because you can fit an infinite number of lines to that point. That means, to us, yes, we found one way one thing could do a thing. And that's great. That means probably in the universe there are more galaxies like this, more places that dinky little black holes are able to remove their gas and effectively kill off their galaxy. But I kind of want to know if that's really common. Is it something you see all the time? If you look at the early universe when all of the star formation seems to be falling off at the same time, Is that kind of thing happening there too? Is it rare and I just got really lucky as a graduate student, or is it common and I just happened to be one of the first people who had instruments available to me to put it all together? Is there a circle of life in the galaxies? Is it a case that these galaxies are going to come back someday? Well, it turns out to do any of that stuff, you actually need to find more. You can't just make all of the answers up with one thing, unfortunately, as much as poor graduate student me wished you could. So I wanted to find new ones of these. And that's actually part of the reason I'm now here, is how do you find them? And the way we did it was we looked at special things about NGC 1266. I told you really early on about ionized gas. In star-forming regions, the hot ultraviolet light in stars are able to irradiate the gas, and that gas is going to re-radiate out in lines. It turns out there are other things that can do that. If, for instance, you shock the gas, that is, you collide the gas into itself, you're also going to heat up that gas, and that gas is also going to radiate. And finally, when a galaxy has stopped forming stars, there is a period of time that's a little bit special, because that galaxy is still going to have some young stars, but it's no longer going to have infant stars. And because maybe you can find that snapshot in time, you can find more of these things. When we looked, we found these were two things that NGC 1266 had. It had shocked gas, and we were able to tell because the energy coming out of a shock makes the gas emission lines look a little bit different than it does when it's coming from star formation. And we could find, through absorption of through spectral absorption, that is, certain kinds of stars have certain gas that's absorbing different lines, different radiation. You find young but not infant stars. And so we formed a team and an acronym, which in astronomy is a big deal. We were looking for shocked post-starburst galaxies, or SPOGs. And I will warn you, you might not take much from my talk today. You will probably remember this acronym. That's what makes it good. Not that it's creative, not that it makes you smile, it sticks in your brain. And so that's what I did, is I looked at a survey of millions of galaxy spectra, and I looked for that special combination that we found in NGC 1266. I looked for the special spectral signatures that told me there was gas in those galaxies, but that gas was not forming stars, that gas was shocked. And I looked for signs in the spectra of young stars, but not infant stars. So not the ones that are going to supernova right now because they're still actively forming. And we found out of millions of galaxies, we had to cut it down to about 100,000 that had high enough signal to noise, that is, they were bright enough for us to actually do this search. We found over about 1,000 galaxies that were like NGC 1266. They were kind of galactic zombies. And because astronomers actually like to share their knowledge, you can actually go and look at the catalog of all 1,067 of these galaxies on our little website. And again, luckily the acronym SPOG will stick in your head, so that website might too. And again, this is just fun. This is all science. There's nothing on there to buy, nothing like that. You just basically get to go look at like thumbnails of cool galaxies for a while, because some of them look pretty wild. Then comes the final phase. So I've told you some of the ways that we have figured out how galaxies trigger their transition and become dead. I've talked to you about the ways that something inside of the galaxy itself can actually cause these galaxies to die. And I've talked to you about how maybe we can find more that are just on this cusp of death where we can learn a lot. But there's something cool about the ones that are the walking dead, the ellipticals and the lenticulars. Those that have already gone through all of these processes, are done with their star-forming gas, and really just are red, don't have young stars. So again, the merger takes the gas out of the galaxy. The merger puts the gas into the middle of the galaxy. The black hole does the rest and gets the gas out of the galaxy. Then, because at some point you can't recover that gas, If you fell into a cluster, that gas is gone, it's now part of the hot cluster halo. You end with just this big bright thing. But these are interesting too, because just because it's red doesn't mean there is not something interesting going on in it, because those stars are old stars. And they're stars that have been around a really long time. So it turns out if we look at those kinds of stars, the stars we see that make up these red and dead galaxies, for instance, in the bulge of our own galaxy, we're starting to learn things about stars that formed towards the beginning of the universe, as opposed to these young rock star supernova stars that are there and gone, but they're not telling us about the beginning of the universe, where some of these can. So here are some of the galaxies. These are, again, NGC numbers, which is New Galactic Catalog. Some of these red and dead galaxies got into Messier's catalog. M87 is a really good example of one. Messier 87 is at the center of the Coma cluster, which is a very nearby cluster to us. And I guess I leave with the more philosophical question here, which is what will become of us? So you might have seen that merger of those two beautiful gas-rich disks that I showed and thought to yourself, we have a gas-rich disk that's kind of next door. I wonder what's going to happen. Well, I will say this is a visualization, an artist's rendition, not a simulation. But let's say in the billion-year future Earthlings who have evolved beyond bodies and now can live sort of immortally, were sitting on Earth. What would it look like to them as time marched on and we met our friend Andromeda? Usually this comes with music. We could not make it work, so I shall narrate. So again, when you look up in the sky, this is kind of what you see. See that right there? I bet you can guess what that is. That's Andromeda. So we're going around, again, this is supposed to be from the perspective of an Earthling, sitting on Earth, moving around the galaxy. Because we orbit the sun also is orbiting the whole galaxy. And watching as we get closer and closer because of the inevitable pull of gravity between the Milky Way and Andromeda. Yeah. Now again, they don't just come together and smash into each other. We're on orbits. But this probably looks like that nice photo on the sheet that you have. That's, again, our future, maybe. But you can also see that now there's a lot more blue, because as these two things collide into each other, the gas is starting to compress, it's starting to shock, it's starting to make super starbursts. But also, unfortunately, that gravity coming from that pesky Andromeda has now thrown us into a really, really bad orbit. We are no longer safely in the disk of the galaxy. We are now getting shot off all over the place in our orbit. It's great for the view, but maybe not so much for us. So again, I turn to my little summary of the different ways you can die in the universe. I know I promised you 100 ways. I apologize. I was going for the gimmick. But I've given you 5 ways. And now, the observer's creed. Obviously, even though we have thousands of galaxies, even though Hubble has revolutionized our world, even though the launch of James Webb is going to do these gorgeous Hubble images, but even further back in the universe and in time, we still don't have all the answers. We found one galaxy like NGC. We found one NGC 1266 that is teaching us a huge amount about what happens after the galaxy is dying and after that galaxy has been doomed to stop forming stars. And yet, we don't know how common that is. We don't know if that's the way all galaxies across all of the universe have died. We do not know if falling into the cluster is the most important part, or if galaxies merge and die in groups before they fall into those clusters. And so, again, I have to say, as an observer, we always need more data. Thank you.
All right. Microphone's on. Good. All right, so we are now at questions. So who has a question, and we'll bring the microphone to you. I guess somebody's phoning in with a question.
You showed an example of the jellyfish galaxy. So my question was, what would cause the gas to be siphoned off in multiple distinct tendrils rather than being siphoned off uniformly all around?
That's actually, so I'm going to assume everyone heard the question because of that awesome cube microphone. So that's because gas in galaxies does not look uniform. If the gas that the galaxy is falling into was completely uniform and smooth, and the gas in the galaxy was completely uniform and smooth, you might expect that. But in both cases, we know that the gas is extremely clumpy. So the fact that you're a clumpy thing that's falling into kind of a clumpy thing, though the gas in the galaxy is probably clumpier than the gas in the cluster, that's why there are tendrils.
Okay, he's got it.
Yeah, in front of what structure are you standing and where is it?
Again, this is unfortunately the Karma Array up in Owens Valley, California, which is now in the valley and has been decommissioned. Yeah. There is ALMA, which is at 16,000 feet in the Atacama Desert of Chile, but I have never psyched myself up enough to go. So really, that's high altitude. But there are telescopes like this on Mauna Kea called the submillimeter array. For anyone who's ever thought to go to Mauna Kea, you can actually see structures like this.
In the case there of the collision scenarios, do we ever get relativistic effects, general relativity effects? You talked about the gradients, the contour lines. Are there gravitational contour lines as we get closer to the center, as they begin to intersect? I realize that these are clusters,
yeah,
and I realize that the majority of the mass is actually dust, not solid objects, but still.
Right. So I will say that I deal on the mesoscale. So most of the scales I'm working on are hundreds of parsecs to kiloparsecs, so 300 light years to 3,000 light years. On those scales, you don't really see those relativistic effects. That being said, there are a couple of very cool scenarios and things that do have relativistic effects. First is, in some of these kinds of galaxies, there seem to be relativistic radio jets that can form. They're called radio galaxies. And in those cases, you actually have such a big black hole that you have basically high-powered radio plasmas coming out, and you can see it really, really far away from the galaxy. The other place that relativistic effects are sort of interesting is that in some of these mergers and these galaxies that are very post-merger, those are actually the galaxies that have such wacky gravitational torques in the centers, you can actually get tidal disruption events, which is where stars fall directly into the black holes.
Yeah, so I mean, the relativistic effects are really strong around the supermassive black holes, and you get that, but that's much smaller scale than she usually deals with here.
Yes.
The actual murder weapon.
It is. And we actually have learned a lot from a couple of these tidal disruption events we've seen. Again, the thing that's super cool is we keep seeing these tidal disruption events in these weird types of galaxies. These galaxies are rare. The kind of zombie galaxies I study are 1% of modern galaxies. And yet, in these events where you're finding these stars that are actually starting to give you an idea of what the black hole spin is because you can actually model it, you're finding them in these weird 1%ers and not really finding them as much in other things.
When the galaxies collide, do And do they actually form new molecular structures when they actually come together? What actually does collide?
For the most part, gas. So the actual stars, for the most part, don't collide with one another. There's probably, I don't know what the chances are. There's like a 1% chance in one of these collisions you have one star hit one star. Yeah, it's lower.
Yeah.
It's very, very small. The gas, on the other hand, actually does collide with each other, and it shocks. And when it shocks, it turns out you do actually sometimes form different molecular structures. But that's because the gas is being heated so much that things like the dust, which has, the dust which was normally pretty happy, is sublimated. And so all of a sudden, the sublimated dust is now gaseous. And so, for instance, in some of these galaxies, but even closer to home, things like protostars, you see things like silicon oxide in the radio spectra because the dust has been destroyed in them from these shocks.
Okay. We have a comment from online. Well, yeah, Grant, get it. That your title is actually correct because 100 in binary is 5.
Whoever that is, like 10 out of 10, man. Well, I guess that's 2 out of 2.
Go ahead.
You characterize the elliptical galaxies as dying, but they seem to have lived long lives. How does their lifespan, on average, compare with those of the spiral galaxies?
I think the thing that always was the way that I always like to think about it is galaxies are like cities. So in, let's say, New York City, you have a set of people who have been living, a nice life that are getting towards retirement age and are pretty happy and pretty calm. But then you also have like the young rock stars and like things going on in those cities. And so in disk galaxies, you still have those star formation events, but that city could be very old. And you just have like the people who have been watching, on their balconies and like smelling the fresh air and thinking about how things were, which is these red stars, are like looking down and seeing the frantic activities of the younger supernova-ing stars. Whereas in the elliptical galaxies, you're basically living in a place where all of the stars are old. So again, Edwin Hubble had it wrong. When Edwin put together the sequence, he thought early types became late types, which is what we call them. Spiral galaxies are late types. I tried very hard not to say it because I think it is confusing. But even in our Milky Way, the bulge of our Milky Way is quite old, even though the disk of our Milky Way on average is young. So it just comes down to the proportion of old to young. They can both have around the same age, but they just have been living and acting differently in those ages. Because again, they're not people, they're cities in this case. So it's the populations.
Okay, we have a question from online. Why do most young stars appear in the galaxy arms instead of the nucleus?
Ooh. Well, I want to think about that because in my systems, they're all in the nucleus because that's where the gas is. And I think for the most part, the young stars follow where the gas is. So it turns out, in the center of the Milky Way, there is a lot of star formation going on. It's called the central molecular zone. There's dense gas there. But the arms is where you're seeing the majority of it. So the answer is follow the gas.
Okay.
Do all galaxies die?
Eventually, yeah. So our universe seems to show a hierarchy. The bigger a galaxy is, the more likely the galaxy is to be dead, which is what caused the pause. So if you're a small galaxy, you probably have had the supply of gas available to you for longer, and it's going to be available to you for longer than a really big galaxy. Eventually, yes. Eventually, it's likely all gas is going to be consumed in galaxies, all stars are going to become white dwarfs, and then they're all going to fall into black holes. But so that to me doesn't seem like quite the answer you want. The answer is yes, all galaxies probably will die, and the bigger, more massive galaxies seem to have died first. And unfortunately for us in the Milky Way, we're coming soon.
Another way to look at it is if you look at the star formation history of the universe, it sort of peaks about 2 to 3 billion years into the universe and has been declining ever since. So the maximum amount of star formation occurred, about 10 billion years ago in the universe, if I remember correctly. That's
Yeah.
it with what you remember?
Range of 2 5 billion years.
Right. So it peaked and then it's falling ever since. So yeah, we're on the decline.
Yeah.
At least from a universal perspective. All right. Other questions? All right. Let's check online. There's something about you talked about Earth, and they're saying you made a doomsday prediction for Earth during the Milky Way Andromeda collision, but then the question is, of course, will Earth still be here during that collision?
Oh, no. By the time that collision happens, the sun will have become a red giant. It will have poofed up big enough that it basically fries us and maybe even envelops us. The stellar winds that are going to be coming off of it at that time will have absolutely crushed us. So no, it will have to be New Earth, or we'll have to be a Star Trek society by then, and whisked around the galaxy to look for places. Hopefully by then we'll have super wormhole networks that can connect us to a galaxy that's not about to collide with Andromeda. It's a really long time from now. We have a lot of time to think about it.
The first pass of the collision is going to be about 4 billion years from now. And the final merger is about 6.5 to 7 billion years from now.
Yep.
So once the Milky Way and Andromeda become an elliptical, it'll be about 6, 7 billion years from now, and our sun will have it'll have done its own dying thing. All right. Any last questions from the audience? All right. Next month, chasing supernova with Kepler. Okay. In October. Irini, stand up and wave. Everyone say hi. You haven't seen her for months. If you would like to go across the street and look out through the telescope in the observatory, follow her. How many can you take?
How many want to go observe me? I'll take all of you.
Okay. There are safety regulations. There's only so many people, and once we got a little bit too much, So, thank you all for coming. Let's give Katey one more big round of applause. We had about a maximum of about 100 people watching live. You'll get about 3,000 to 5,000. How you doing? Thank you for coming over. This has been months and months.
I know, the weather's
It is not been very helpful. Yeah, why don't you wait over there because people always come to the